Welcome to Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at our second set of notes over Chapter 10. Mainly, we're looking at three different things. Other applications of the ideal gas law. We're also going to look at gas stoichiometry, and then finally, we're going to look at another type of shortcut we can use when we know the amounts of gases. But to start with, gas law is an incredibly important, the ideal gas law that is an incredibly important idea in gas laws because most all of the gas laws that we look at really can be derived from that one fundamental law. Now, another thing that we can do besides deriving Boyle's, Charles, Gay-Lussac's, and the others is to do substitutions into the ideal gas law to obtain other forms of the ideal gas law. And what we're going to look at is actually something that's on the AP constant sheet, the relationship between molar mass. So one of the equations on the constant sheet is that the molar mass of a substance is related to the mass in the moles. Now on the constant sheet, it basically solves this equation for n. So n would equal the mass of the substance divided by its molar mass. So then molar mass would equal the mass over the moles, which makes sense if you're thinking about it. Units of molar mass are grams per mole. So if we take the mass of the substance in grams and divide it by the number of moles, we would get grams per mole, or molar mass of a substance. So if we rearrange this to solve for n then, like you'd see it in the equation sheet, mass divided by molar mass equals the number of moles, and that we can substitute into PV equals nRT to obtain this form of PV equals nRT. And if we were directly solving for or given the mass of a gas and we knew the molar mass, we could use this in the equation rather than solving for moles. But that's not really the final form of the equation that we're looking at here. The next thing we're going to do is we're going to rearrange that equation from a molar mass point of view. So the molar mass is going to equal mass times R times T over PV. Now notice in this particular form, we've got a mass on top and a volume on the bottom. What is mass over volume? Well, that equals density. So we can now substitute density in for the mass and volume, and we obtain this form of the equation. And if we rearrange this slightly so it looks like our PV equals nRT or our perv-nert form, we get our pim-dirt form of the ideal gas law. The pressure of the gas times its molar mass would equal the density of the gas times R times T in Kelvin. And we can then use pim-dirt to deal with density molar mass type situations. The key to when you use pim-dirt, if it ever says or asks anything about density, you're going to be using this form of the ideal gas law, the pim-dirt form. Now, next thing we're going to look at is gas stoichiometry. Like all stoichiometry, if you see a balanced chemical equation in the problem, chances are that means that equation is going to be used for stoichiometric calculation. So keep in mind, if you ever see in a homework problem you're working on, or a problem on the review, or the problem on the test, if you see a balanced equation, think this is probably a gas stoichiometry problem. Now, remember in stoichiometry, you're converting from moles of one substance into moles of another. So you fundamentally always have three steps. You get to your mole step to go moles from one thing to moles of another, in the mole ratio step in the middle, and then you get out of mole step at the end. Now in gas stoichiometry, really what we're going to be using is PV equals nRT to get to moles or to get out of moles. So really, the only question in gas stoichiometry is which do we do first? Do we do PV equals nRT and then stoichiometry, or do we do stoichiometry and then PV equals nRT? So let's say we've got a PV equals nRT first type problem. So really what we're going to be doing is our step one, get to moles. We're not going to use molar mass or something else. We're going to use PV equals nRT. We'll take a given pressure, volume, and temperature and use PV equals nRT to calculate what the moles are. So that's how we start the problem. And then we can do steps 2 and 3, moles of one substance to moles of another, and then get out of moles. Typically what they're going to ask us usually do is get to the mass of substance B. So it would end up looking like this. In our step 1, our get to moles step, what we're really doing is our PV equals nRT calculation. And then once we know moles, we can do steps 2 and 3, our mole ratio and our get out of moles step. And like I said, usually they'll be asking you for the mass of one of the other substances in the reaction. Now, the other type of gas stoichiometry situation is when they typically give us the mass and they're asking us to find out moles of another substance B that's a gas? Well, what we can do is we can use PV equals nRT at the end to get to our temperature or volume or pressure of the other gas. So what we're going to do now is do PV equals nRT at the end. So we take the mass, convert it to moles using molar mass in step 1, convert moles of one substance to moles of another substance in step 2, and then we can plug that mole amount into PV equals nRT to take and solve for our unknown variable, the pressure, the volume, or the temperature. Now, one thing about gas stoichiometry is sometimes it's actually much faster than you think it is. There's this thing called the Avogadro's law shortcut. And what we're really going to do is use the mole ratio as a volume ratio. So if you're ever asked for a gas reaction where you're asked to find the volume at a constant temperature and pressure. That's really the key to this situation. If they're asking us for the volume and we're at a constant temperature and pressure throughout the reaction, we can do an Avogadro's law shortcut to prevent from doing something like a PV equals nRT, then a mole ratio step, and then another PV equals nRT. We can do all of that in one quick relationship. Based upon Avogadro or the ideal gas law, if we're at constant temperature and pressure, V1 over N1 has to equal N1 over N2. So we can use the volume ratio as a mole ratio in a stoichiometry problem. So we can take what would be a multi-PV equals nRT and stoichiometry and convert it into a simple one-step dimensional analysis problem. So here's something, a type of problem where we could use this shortcut. The decomposition of ammonia proceeds by the following reaction. Notice we've got ammonia gas that's being converted into nitrogen gas and hydrogen gas. And then it goes on to give us the fact that if 4.0 liters of ammonia decomposes at 102 kPa and 25.0 degrees Celsius, so they've given us a volume, a pressure, and a temperature. And they're asking us from that much ammonia what volume of N2 could be produced if the temperature and pressure remains constant. And that's a really critical idea here, that the temperature and pressure are constant. So we could use PV equals nRT to calculate the number of moles of ammonia. We could convert that from moles of ammonia into moles of nitrogen doing stoichiometry. And then we could do another PV equals nRT to take that mole amount, that temperature, and that pressure and find out what the volume is in liters. So literally, a stoichiometry plus 2 PV equals nRT. Or we can do it just as a one-step problem. Remember, the mole ratio is also a volume ratio in temperature and pressure problems. So we can go straight from the volume of ammonia to the volume of nitrogen gas using the stoichiometric relationship between the two. If at constant temperature and pressure the volume ratio is the mole ratio, we don't have to do the stoichiometry by going through moles. We can go straight from volume of one to volume of the other, and we're done. It's literally that easy. And keep in mind, if they ask us for the hydrogen, it would just be a 2 to 3 ratio here, because it's 2 liters of ammonia for every 3 liters of hydrogen. And honestly, by the same token, because moles are additive, if they gave us the volume of the ammonia and they ask us what the total volume would be, I know for every 2 moles of ammonia, I have a total of 4 moles being produced, 1 mole of N2 and 3 moles of H2. So I could go from 2 liters of ammonia to 4 liters of total gas using the same mole as a liter ratio. So we can go from liters of ammonia to liters of nitrogen, liters of ammonia to liters of hydrogen, or we can also go from liters of ammonia to total moles using a 2 to 4 mole ratio. Now, the last idea that we're going to look at here is really Dalton's law type relationships, and then a little bit related to partial pressures and total pressure, which is like Dalton's law, but it's a little bit different. So in a Dalton's law of partial pressure problem, you need to understand the total mixture of gases is going to equal the sum of the individual pressures. So gas pressures are additive. Each gas pressure exerts a distinct pressure on the total container. And if we sum all of the partial pressures or individual pressures, we would get the total pressure the mixture of gases exerts. So in other words, it's a fairly simple law. The total pressure of a mixture of gases equals the sum of their individual pressures. So if we had 2 gases, P1 plus P2 would equal the P total. If we had three gases, it's P1 plus P2 plus P3. And remember, these represent the partial pressures, the partial pressure of gas 1, the partial pressure of gas 2, and the partial pressure of gas 3. And we call them partial pressures because they're part of a total when we have a mixture of gases. Now, one specific application of Dalton's law is called the Dalton's law correction. Anytime you see the phrase in a problem collected over water, and this is typically how we collect gases, is we use water displacement. So we fill a test tube or a beaker with water, and then by bubbling the gas into it and displacing the water, we end up collecting the gas. And you need to understand the consequences of this type of collection. When you collect a gas over water, the pressure inside the container, in this case, the pressure of the gas inside this beaker here, is not actually the pressure of the pure gas. It's a pressure of the gas plus the water vapor that gets mixed in. Because anytime we have water, water evaporates, and at constant pressure, it evaporates at a constant rate. So we can actually use a table to determine at a given temperature what the vapor pressure of water is going to be inside that beaker. And you need to understand, if we measure the pressure of that gas in the beaker, it's not a individual pressure. It's not the pressure of just the gas. It's a total pressure. It's the pressure of the gas we collected plus the pressure of the water vapor that's in there. So we have to do what's called a Dalton's law correction. So to find only the pressure of the desired gas, we have to subtract out the water vapor. So since it's a total pressure situation, P total equals the pressure of the gas plus the pressure of the water. So the pressure of the gas would be P total minus the pressure of the water. And every time you see that phrase, collected over water, that means we're going to do a Dalton's law correction. This would actually give us the pressure of the gas we collected. Now, another thing I want you to understand, because this is a common idea that sometimes pops up in FRQs, and it's definitely something we're going to end up using in labs in this chapter. You need to understand the consequences of the situation here from a pressure point of view when the liquid level inside this beaker is the same as the liquid level outside the beaker. At that point, when the water level inside our beaker is the same as the water level around the beaker, it has to be true that the pressure of the gases inside the beaker are going to equal atmospheric pressure. And in this case, since it's collected over water, it's really a P total. That's why I put PT. So if we can measure the atmospheric pressure, I know the pressure of the gases inside that container. I know P total because it's going to equal atmospheric pressure. So whenever you have liquid levels inside and outside equal, that means the pressures inside and outside are also equal. And that's a concept that you really should know, because we're going to take advantage of that in the molar volume lab that we do. Now, the last thing we're going to look at here is the relationship between partial pressures and mole fractions. And this is actually a shortcut that we can use to avoid doing, once again, some multiple PV equals nRTs. So the situation here is we have a constant volume and temperature. Now, normally we would compare the pressure and the number of moles of a gas before and after. That's not really what we're looking at here. We're going to compare the pressure of a substance to the total pressure. So we're actually looking for a relationship between partial pressures and total pressures and amounts in moles. So here's the situation. Now, where this comes from is, remember, PV equals nRT. So I'm going to start with that. The pressure of 1 times the volume of 1 equals the N of 1 times R times the T of 1. If we solve this for pressure, we're going to get N1 R T1 over V1. Now, that would be true if we had one gas. Now, if we had a mixture of gases, it would be true that the total pressure times the total volume would equal the total moles times R times the total temperature, or the temperature of the system. So we can also solve this for P, but now we're solving it for P total. Now remember, if we solve this for P1 and get this equation up here, I can maintain the equality as long as I divide both sides by the same thing. Well, if P total equals N total, R total, T total over V total, then they equal each other. And I'm maintaining the equality if I divide this side by PT, and PT is the same as nRT over V. So what I've now established is, after I cancel the nRT, and what I'm left with is going to be P1 over P total is going to equal N1 over N total. Kind of like I did before with the same gas under initial and final conditions. P1 over P2 would equal N1 over N2. But now what I'm relating it to is not the same gas, just under different conditions, but I'm relating the pressure of one of the gases and its number of moles to the total pressure and the total number of moles. So what we've really done is we have looked at the relationship between the partial pressure to the total pressure and the partial number of moles to the total number of moles. Now, this is what's known as the moles of the one substance compared to the total number of moles, is what's known as the mole fraction. And the symbol for that is this Greek symbol here, chi. So N1 over N total would equal chi1. And all that really means is the mole fraction, the number of moles of our one substance divided by the total number of moles. So if I write that as an equation and solve for my partial pressure of 1, I get this. The ratio of moles, the partial number of moles to the total number of moles, times the total pressure has to equal the partial pressure. So if I know my amounts of my gases and I can calculate their moles and I know the total pressure, I've got a simple relationship from the total pressure to the partial pressures using this mole ratio. So I can go from literally what would be multiple PV equals nRT calculations down to 1. Now the trick is P1 is going to equal then the mole ratio, chi1 times the total pressure. If I knew the moles and I knew the total pressure, I could easily calculate the partial pressure. This is a shortcut that you will use whenever you see you have multiple gases with amounts at constant volume and temperature, and they're giving you the total pressure. So if I know what the total pressure is given in the problem, and they tell me my masses of my 2 gases or 3 gases, I could easily convert those to moles, and using the mole fraction, the moles of the one substances over the total moles, times the total pressure to calculate the partial pressure of the first gas, without having to do a PV equals nRT calculation. So this is, and so volume and temperature wouldn't even have to be given. And if I wasn't given the volume and temperature, I couldn't use PV equals nRT in the first place. So if they tell me I've got constant volume and temperature, but don't give them to me, I've got no way to do this without using this shortcut, using PV equals nRT. So remember, look for this whenever you're given amounts at constant volume and temperature, and they tell you the total pressure. You can quickly calculate the individual pressures in that situation. And that ends our second set of notes over Chapter 10.